We have been talking about the magnetic fields generated by moving charges and by currents. And it's time now to investigate the effect of those magnetic fields back on other charged particles. So, how magnetic fields exert magnetic forces on moving point charges. First off, here's what we're not going to be discussing at the moment. We're not going to be discussing the magnetic forces you're probably most familiar with already, the forces between magnets, like bar magnets, or between a magnet and a fridge. A couple of bar magnets like this are magnetic dipoles. We see that characteristic dipole field that a bar magnet generates. And like poles of two dipoles will repel, north poles repel, opposite poles will attract, a north pole and a south pole will attract. And you are familiar with how those forces between a couple of magnets like this, they can tend to be very weak when the magnets are far apart from each other. But as you bring the magnets close together, say two magnets you're expecting to attract, there's very little force, very little force. And then all of a sudden, once they get close enough, suddenly there's a large force that yanks them together and they snap together all at once. That's because this force versus distance graph for the force between magnetic dipoles is a 1 over r to the fourth function. Drops off rapidly as they get far apart from each other, and conversely increases rapidly all of a sudden when the magnets are close. I haven't derived this. I'm not going to derive this, but I'm mentioning it because this is what you are already familiar with as far as behavior of magnets that you've played with. Also, a little fridge magnet like this has a north pole and a south pole. It too is a magnetic dipole. And it'll be attracted to the surface of your fridge because the fridge is a type of material called a paramagnetic material. We're not going to be discussing this sort of thing right now either. So, in fact, some of what I'm going to go on to say in the topics we are discussing may seem to contradict what you are familiar with from playing with everyday magnets. Don't worry about that for now. We'll eventually come back around to discuss these phenomenon. But we're starting with something different, something simpler. The effect of magnetic fields not on dipoles, but on individual charged particles. That's our real subject right now. Okay, so here's what we are going to be discussing. Comparing gravitational forces, electric forces, and now magnetic forces. We know from Newton's law of gravity that the gravitational force on a point mass in a gravitational field is given by this expression. If you have a mass in a gravitational field, that mass experiences a force. Likewise, Coulomb's law for electric forces. If you put a point charge into an electric field, then that charge in that field experiences an electric force. Magnetic forces are similar, but with one key difference. A magnetic force depends not just on there being a charge and a field, a magnetic field, but it also depends, interestingly, on that charge being in motion. And there's a cross product. The velocity of the charge crossed with the magnetic field will determine the direction of the force. So the force depends on how big the charge is, how fast it's moving, how strong the field is, but also the relative direction of the velocity and the magnetic field. Let's look at some examples. Again, I haven't derived this. I'm not going to derive this. This is observed in nature. So this is new physics for us right here. All right, suppose we've got a uniform magnetic field pointing to the right throughout this region. Here we have a positive charge with a velocity initially to the right, and we can find the magnetic force on this charge. So we're going to do V cross B. Take the velocity crossed with the magnetic field. Oh, but V is to the right and B is also to the right. So if we want our magnetic force here on that particle, Q V cross B, well, two vectors that are parallel to each other have an angle of 0 between them. Sine of 0 is 0. Cross product is supposed to be the product of the perpendicular parts. These two vectors have no perpendicular parts. So that cross product is 0 in this case. There would be no magnetic force on that particle. From Newton's second law, the acceleration of that particle being given by the magnetic force divided by its mass, no magnetic force, no acceleration. Therefore, if you send a particle moving in the same direction as a magnetic field, sort of moving parallel to a B field line, it will continue to move with a constant velocity. No force if you're moving along with the B field. Quite different from putting a particle into a gravitational field or an electric field, which always exerts a force parallel to the field or anti-parallel to the field. Here, moving with the field, no force at all. Okay, next example. Here we've got a positive charge and a negative charge, both initially with upward velocities, say in the y direction here. Let's consider the positive particle first here. So we want to find the force QV cross B. So our V vector crossed with our B vector. Thumb is going to point into the page from right-hand rule. V cross B, thumb points in. This one is going to feel a magnetic force pointing into the page. Negative charge particle, V cross B once again. So V crossed with B points into the page. So V cross B is into the page, but if Q is negative, that negative sign flips the direction of this vector. So this particle here is actually going to be experiencing a magnetic force. V cross B is into the page, but the negative flips it, so a magnetic force out of the page. What we'll find in a moment is that this positive particle is going to start circulating, moving in a circular path, looping around one of these B field lines, like using the B field line as an axis around which it's rotating. And the negative particle will be doing the same, moving in a circular path, circulating around one of these B field lines, but rotating in the opposite direction relative to that positively charged particle. More on that coming up next. Okay, third example over here. Suppose we've got a positively charged particle with some velocity initially at an angle like this to the B field. Okay, let's break that velocity up into its components. There is a Vx component and a Vy component here. If we want the magnetic force on that particle, QV cross B, okay, well, the x component results in no magnetic force since the x component is parallel to B. Our y component, that's the part that's perpendicular to the B field. So V cross B, that'll be Vy cross B. Thumb points into the page. So as a result of this Vy cross B, we're going to have a magnetic force into the page. Let's see here. I guess the magnitude of our magnetic force would be the magnitude of Q times the magnitude of V cross B. Here we want the product of the perpendicular parts. So that would be Vy times the magnitude of B. We could also express that if we call this angle theta right here, we'd be noting that Vy is V sine theta. And we have a magnetic force into the page. So I guess we could write sort of in summary here that the magnetic force at this moment would be the magnitude of Q times Vy times the magnitude of B, and it would be in our negative Z hat direction, pointing into the page. X, Y, Z is out of the board, so negative Z into the board. Okay, as a result of this, this particle has an x component to its velocity that's not going to change. The x component will be constant, like in our first example way over here. So Vx is not going to change. No acceleration in the x direction if there's no force in the x direction. So this particle will continue to drift to the right parallel to that field line, while at the same time, because of the component that is perpendicular to the B field, it will begin circulating around one of those lines like an axis. So the combination of those two motions will result in a helical path as the particle drifts to the right while circulating around the magnetic field. More on that later. Okay, let's look at some examples from kind of a different perspective. Let's say instead we've got a B field pointing into the page, and it'll be a uniform B field in the page. I'll pause here.